Okay, so with the cross product out of the way, let's get back to talking about the magnetic force and how it acts on a moving charge or a current carrying wire. So we talked before about how you can have a wire going from one point to another, and we're going to define the vector displacement the wire carries you through as L, vector L, and then we're going to put I in place, and we're going to say I is the current on the wire. So actually, let me draw it up here. We'll say the current along the wire is I. This is the direction positive charge is moving. We're going to say it's moving the same direction L is pointing. And then the magnetic field is, let's see, the magnetic field is going this way. So we're going to have a nice uniform magnetic field. If it's not uniform, you have to integrate, but screw that. We're not going to do that. So the magnetic field is usually represented by the letter B, the capital B vector. I have no idea why, frankly. I suppose at some point maybe I'll find out, but right now I have no idea why. And so the force acting on this wire is going to be perpendicular to the magnetic field and perpendicular to the current. It's freaky that way, and the force is going to go in that direction. And so the force is going to be given by, this is going to be for a force on a current carrying wire is going to be, the force is going to be equal to, wow, that's ugly already. Let's see. Force is equal to, that's a little better, I times L. So this sort of represents the amount of current and its direction, motion type thing, and the cross product of that with B. So there you go. This follows the right hand rule. So if you can take your right hand and imagine your thumb pointing the direction of the current, so the thumb pointing this way, and then fingers pointing this way, or you have your index finger pointing this way, then you would take your second finger and it would point up, which is the direction of the force. But actually there's a much easier way to use the right hand rule for magnetic force. The way you do it, and let me see if I can actually sketch out a hand here. So there's your thumb pointing in the direction of the current. Okay, so there's your thumb pointing in the direction of the current, and then your fingers point in the direction of the magnetic field. And these are, of course, horribly deformed fingers, but that's the best I can do. And there's the rest of your hand, kind of. Okay, so now your fingers are pointing in the direction of the magnetic field. And here's the cool part. Do this, and if this is your right hand, this side here is your palm, which means the direction you can push with your right hand, with the palm of your right hand, is the direction the force goes. So this is for a positive current going this way. So if you have a current going this way, and the current is positive, so it's got to be greater than 0, and you have a magnetic field like this, then you can use the right hand rule. This is your right hand, and you can use that to find the direction of the force. Very easy. Yeah, okay, so let me move on and talk about a moving charge. This is not much different. So let's say you have a charge here, and it has a positive charge, plus Q, and it is moving, and I'm going to denote its movement with a velocity arrow. Okay, so it's got some velocity vector, and of course it's moving through a magnetic field. Well, this isn't too hard, I think, intuitively to see that a moving charged particle is the same as a current, in a sense. And so what you can do here is, if you want to draw, sort of an analogy between these two, or a parallel, is say, well, this current is a representation of how much charge travels over a period of time, right? So the current is an amount of charge traveling over a period of time. Okay, so imagine now that instead of, say we pick some delta t, instead of this current carrying this amount of charge over this time delta t, we're going to say the whole charge is in one lump, and it travels there, in one chunk in some time delta t. So, what then is the velocity of this charge? We want it to cover the same distance it would in the wire, but instead of being strung out and going a bit at a time, it's going to go all in one lump. This whole plus q charge is going to go there. So what's the charge's velocity? Well, if we say it takes time delta t to get there, then what you could say is that velocity is equal to the displacement, right, divided by delta t. And furthermore, so you've got this here is the current, how the current relates to the amount of charge and the time it takes to travel, and this is the length of the wire versus the velocity of the charge and the current. So now it's very easy to just substitute in, well, let's see, you have to rearrange this into L equals V delta T, right? But then you take this, and you substitute them into F equals IL cross B, and what you get is F equals, so your I becomes Q over delta T, right? Actually, I'm going to draw it down here, okay? So F equals, and you take your current, which is Q over delta T, and that it gets multiplied by your distance, which is velocity delta T, and then it's all crossed by the magnetic field again. And then it's not hard to see that if you pick, let's say, yellow, the delta T's will cancel out, and then you'll get F. This is the force acting, that's also a vector. This is the force acting on a moving charged particle is QV cross B. Pretty easy, huh? So this is, this is just how you get from one to the other. These are basically the same thing. It's just sort of, how can you call it? Talking about, you're talking about it a different way. Here you're talking about the current traveling over a distance at some constant rate, and so there's constant force on it. Here you're talking about an object with one charge moving through a field, and it's the direction of the magnetic field, the direction of the force. No surprise, of course, the force goes the same direction. You again have the right-hand rule. Same deal, really. So you can apply the right-hand rule again. So one final question we have to ask ourselves is, what is the unit for a magnetic field? Well, I don't want to erase that. So what's the unit for a magnetic field? Well, this is not terribly hard. It turns out we need a new unit for the magnetic field, and it's called a Tesla. So the unit is a Tesla. It's abbreviated capital T, Tesla. It's named after the Russian scientist Nikola Tesla. I think he was Russian. Nikola Tesla, and he had these ideas about having, if you've heard of Tesla coils, he had these ideas about having these huge metal coils that would sort of harvest electricity from the magnetic field of the Earth. Kind of bizarre, and I think he was a contemporary of Edison, and it turned out that Edison's ideas worked much better. But there you go, Nikola Tesla, named after him. And then also there was the cheesy some metal band in the 80s, I think, called Tesla. But anyway, so let's take the units for, we can pick one of these equations. They should come out the same, right? So let's take the units on this equation and go with newtons is the units for force. So I'm sorry, I should explain. We're trying to figure out what the hell a Tesla is, right? So a newton has to be equal to a coulomb. Okay, that's the unit of charge. Unit for velocity is meters per second. And then when you do a cross product multiply, you just multiply like normal. Because units are all scalar. So B, the magnetic field, is in Teslas. So now we can figure out what a Tesla is. What this turns out to be, if we do this all correctly, is that a Tesla is a newton over a coulomb times a meter per second. Now a newton per coulomb, is this right? Coulomb, meter per second, Tesla equals newton. Well, a newton per coulomb is also a volt per meter, right? This is just an electric field unit, right? So a volt per meter times a meter per second. So Tesla is actually a volt per second. Is that right? That seems strange to me, but what I'm going to do is I'm going to bring this one down here and do it too. So a newton equals an ampere, which is our unit of current, times a meter, which is our unit of distance, and then times a Tesla. So this means a Tesla is equal to a newton per ampere meter. And where do we go from here? Is that right? Yeah. An ampere is a coulomb per second, so this is a newton second per coulomb meter, and a newton per coulomb Wait a minute. Now I'm getting it wrong. What did I do wrong? Let's see. Oh, I kept meters per second here instead of inverting. Ah, that's what it was. Okay. So, well, just to prove that I don't always, edit these things before I do them. So, this should actually be a Tesla should be a Newton per Coulomb second per meter, and then you really can't reduce it much. That makes more sense, and this is what we got over here too. Okay, so this is the definition of a Tesla: is that 1 Tesla is a Newton per Coulomb times a second per meter. Maybe you can think of that as over a meter per second, or whatever you like to think. You could also write it maybe as 1 Tesla equals. So let me actually get rid of this purple crap here. You could also write it as 1 Tesla is a. You could also write this as a. Let's see. So it's a Newton over a Coulomb meter per second. If you like that a little better, maybe that's a little more appealing to you. Or maybe I don't know. We could say a volt per meter squared times a second. Who knows? You've got your choice of many wild and wacky and interesting ways to write a Tesla. One thing to note is that there's also one other kind of unit for magnetic field called a Gauss, and a Gauss is the unit that's used in the CGS system, which is a system based on centimeters, grams, and seconds. The SI system the SI system we normally use is called the MKS system. It's based on meters, kilograms, and seconds. The CGS system is based on centimeters and grams. So it's also metric, but they end up with different sized units. And a Gauss is their unit of is the CGS unit of magnetic field, and it is equal to 10 to the minus 4th Teslas. And the reason why this is important is because people will often express it in Gauss because 1 Tesla is a freaking huge unit of magnetism, or of magnetic field. I think actually it would be fairly difficult to construct a magnet with a field of 1 Tesla because the internal forces in the magnet would tend to sort of crush it. So that's why the Gauss is often used. So anyway, now you know. Oh, I've got mail. Yay. Now you know what a Gauss is, you know what a Tesla is, you know the right-hand rule, you know how to apply magnetic force to something. And so what I'm going to do next is look at a couple of examples that will hopefully sort of crystallize this stuff and make it a little easier for you to understand how this is used in practice. So that's coming up.